Hello everyone, welcome to our class. Now let's study Chapter 5, Finite Time Thermodynamics. The first section, Finite Time Thermodynamics. At the first, let's do some comparison of thermodynamics and heat transfer. The properties in thermodynamics always in equilibrium state, no relationship with the time, as we know. However, in heat transfer, the properties is always not in equilibrium state, always temperature difference existence. So it's different, thermodynamics and heat transfer is different for the properties. Another one is process. In thermodynamics, Q and W is relative to the processes and states. However, in heat transfer, Q is relative to the processes. The third one, heat, the unit. In thermodynamics, is joule and kilojoules. However, in heat transfer, the unit is watt and kilowatt. Kilowatt is relationship with the time. Now, let's have a review about reversible engine. In thermodynamics, we have learned the Carnot cycle. In PV diagram, we can find the Carnot cycle consists of 4 processes. From state 1 to state 2 is temperature is constant. From 2 to 3, adiabatic process. 3 to 4, the temperature is constant. From 4 to 1 is a adiabatic process. We never discuss the time because we think the state always is equilibrium state. So we do not consider the process. However, for a real process or real engine, as we know, any real thermal process is irreversible. Any engine is not completely reversible. The heat transfer enters engine or goes out from the engine to the environment. It cannot be completed in moment. It requires a range of time. That's to say, any active engine cannot work under a complete balanced state as the ideal Carnot engine. So we have to consider the heat transfer speed. Here is an example to consider the process time. Here is a Carnot cycle. 4 processes consist of the cycle. 1 to 2, 2 to 3, 3 to 4, 4 to 1. For example, from 1 to 2 need time T1. From state 2 to 3 need time is T2. 3 to 4 need time T3. 4 to 1 need time to 4. So the total time in a cycle is T1 plus T2 plus T3 plus T4. If we understand the output, the total work is W. Here, W, the unit is kilojoules. Therefore, the total power out. Please remember, work and power is different. So the power is W point equals W over T. T is total range of time. Equals W over T1, T2, T3, T4. Here is the power. Power, the unit is kilowatts. Okay. When we understand the energy enters engine needs some time, how does the heat energy go into the heat engine? How does the heat energy goes into the engine? Certainly, it will meet some resistance in the processes. That's to say, the temperature of the heat energy inputting the engine is not T1, but T3 from this picture we can find. Because from T1 to engine, there is a heat resistance, G, heat resistance. So there is some temperature decrease. At the same thing, the temperature of the waste heat energy outputting the engine is not T2, but T4, because from engine to the environment to cool reservoir, there is a heat resistance, make a temperature decrease. Also, for convenience, established another concept, just assumption of endo-reversible engine. We know the heat transfer between heat source and the engine is not complete free. Certainly make some non-zero heat resistance. There is some temperature decrease, so produce some temperature difference. However, for convenience, we still think that all of the irreversible is produced in the heat transfer process. It's not in the engine. We can think the engine is still reversible. All of the irreversibility just made by the heat transfer. If this assumption is right, we can think this system just is endo-reversible engine. We think its internal engine is still reversible. That's endo-reversible engine. It's very special concept.